start this. Okay, so y'all picked up your piece of paper, and then you have two other markers. And so you'll turn your paper straight up and down like this, so tall wise. So what we're going to do is review, or actually kind of really solidify those items that we talked about at the end of class yesterday, which was p-value, alpha, statistically significant, p-value being low, all that kind of stuff, okay? And so I figured out a picture that I want y'all to be able to draw, or that we're going to draw for you to understand. Okay, so I'm going to use three different colors just like you have. I'm going to use black to represent your pencil or your pen. So we'll start off with just you writing with something regular like your pencil or your pen, and then we'll go to other colors. So the very first thing that we're going to do is define p-value. Okay, and we're going to define that in terms of the song. So I'll kind of sing things as we go along, because you really do need to be able to know word for word this definition. Okay, so p-value is the probability. So p-value is the probability dun, 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 of getting this sample or something more extreme. So p-value is the probability of getting this sample or something more extreme if the null is true. Okay, so that's the definition of p-value, and we're going to draw that shortly so you can see a visual of what that is. Okay, so we're going to play the video of it and let you sing it. Actually, you know what? I think I'll save the song for when we have the picture of it, so we can look at the picture of it as we're singing it and kind of make that connection. All right, one other thing I want to define up top is alpha, and that is the size of the rejection region that your sample may fall in. Now, this value is given to you, or you default to 0.05. So that's the size of the rejection region. Rejection region. Okay. So now what I'm going to do is I'm going to show you the whole piece of paper, and we're going to put two normal models on there. So take your remaining section and kind of split it in half, and we're going to have a normal model on the top half and the normal model on the bottom half. You do want to have the ability to write underneath the normal model a little bit. So split that remaining section in half. Yes. Oh, I said 0.5. I mean 0.05. Sorry. That default, thank you if I said that incorrectly. The default alpha is 0.05. Okay, thank you. Okay, so there's our normal models, and so here at first we're going to kind of be drawing the same thing on both of these. All right, so the same thing on both. We're going to say that both of these normal models are centered around the claim of the null hypothesis. And since in this chapter we're doing proportions, then we know that our data, our center of all the p-hats would be around what is told to us, the mean of the proportion, population proportion. So the center of all the p-hats should center around that population claim p. Okay, So I want us to draw p-hats in there. So if that null hypothesis is right there, then we should have all these little different p-hats in here. But most of them, you have more of them in the center. Okay? They're focused and centered around where the null hypothesis is. So just draw yourself some p-hats in both of these curves. Okay? So then I want you to kind of draw, where we kind of typically said 2 standard deviations. We're going to find that rejection region can change size, but that's where we pretty much anticipate most of the items will be centered around. And so we're going to write something about both of these curves. So I'm going to write something about this one, and then this one also. I'm going to write the same thing. Okay. So I'm about to write something about both of those curves. And I'm going to zoom in so that I have room to write what I want to write. Okay. So what I want to tell you is that if the null is true, then the p-hats are centered around that mean of p-hats equals p. Okay, so on both of those curves, if the null is true, then your samples will be around the null hypothesis. Okay, if it's not true, they're not. They're shifted over. So if the null is true, then that's what all your p-hats are looking like. They are centered around that null hypothesis. And then I also wanted to write, why are there all these many different p-hats? There are many p-hats because what? Good. Of sampling variability. See, what happened was you got different data than I did. Randomness, you randomly got a different sample than I did. So because of randomness, you got different data, which made your sample different, sampling variability, but they're all going to be around the null hypothesis. Okay, now let's change colors. I'm going to change to red, and on both of these curves, we're going to put the rejection region in here. I'm going to pretend that this is a problem about where the alternative is less. So we think this is the center, but we're concerned that it might actually be lower. So I'm going to put all of my rejection stuff on the lower tail. Tomorrow we'll talk about how to do it on 2 tails. Okay? But for today, we're going to do this. So I'm going to say that this section over here, I'm going to draw just this one rejection region. Okay, so once you passed your little, where most of them are centered, where you drew that line, there's my rejection region. And this line, this is your alpha. Okay, that's your alpha value. And that is the size of, and so I'm going to label on both of these curves that this is the size, that this is the rejection region. there's my rejection, the size of my rejection region, whatever size they told me alpha was. Okay? If samples fall in there, if I get a sample in there, then that's going to make me reject the claim, the null hypothesis claim. Okay, so up until now, both of these are the same. Both of these pictures look the same. But now we're about to make them have something different. So I'm going to change over to the color blue, and this is going to be, I'm going to put in the sample that I get. Okay, so hypothetically, this is what's going on. I'm about to now go and take a sample. Okay, so I'm going to sample. The top curve is going to have my sample is not going to be in the rejection region. My sample is going to be, say, maybe this value right here. Okay, so I'm going to put my blue p hat right there. Okay, so not in the rejection region, closer to the center. I'm going to have on the bottom curve, I'm going to put my p hat in the rejection region. Okay, so I got a sample that is down here on the bottom. I got a sample that is in the rejection region. Okay, so I got a sample that is in the rejection region. So now we're about to put in the p-value. So let's sing our song, or talk about what we know it is. The p-value, let's do the top one, top curve. The p-value is the probability, and probability is a shaded area. So p-value is a shaded area. It's the probability of getting what? This sample, or what? Or something more extreme if the null is true. So if the data is really located all right here, then let's draw it. Draw a little dotted line. I'm going to draw a dotted line down where my sample is that I got, and I'm just going to kind of do a little curly Q because I still want to be able to see the red. You should still be able to see the red because we got to compare it. Okay, so the blue, all of this blue area is my p-value. It's the probability of getting that sample or something more extreme if the null is true. Okay, so while you're drawing that, we'll look at that here and we'll sing our song. Okay, so let's see. Ooh, we don't want that one. No, we want this one. Okay. Okay, so let's visualize our p-value while we're singing the definition. Do you remember when we used to sing the p-value is the probability of getting this sample or something more extreme if the null is true? Alright, so there's our p-value, and we'll save that one. So our p-value is that probability of getting the sample we got or something more extreme if the null is true. So let's discuss the qualities of this p-value. Okay, so I'm going to draw an arrow and point to my blue shaded area. So I want you to compare the blue shaded, the size of the p-value, the blue in my case, to the size of the rejection region, which is alpha. So how does my p-value probability compare to my alpha probability? In this picture, it's what? Bigger. Good. There is more p-value than rejection region. So the p-value is greater. And the key is that is happening because the sample that we got is not in the rejection region. See? So if the p-value is bigger than alpha, then the sample that we got is not in the rejection region. And so it's actually not statistically significant, and we'll talk about that in a minute. Okay, so if it's not in the rejection region, the sample we got is happening just because of sampling variability. So do we have evidence to dispute the null hypothesis? Do we have evidence to reject the null hypothesis? No. So we fail to reject, we do not have evidence to reject the null hypothesis. Okay? So this is the main point for this top picture. That is the main information that you need to know about that top picture. We fail, our p-hat was not in the rejection region. Our p-value is greater than alpha, so we fail to reject. Now, I do want to take a moment and tell you the king of all dirty words in statistics is saying the null hypothesis is true, or I accept the null hypothesis. You cannot say you accept the null hypothesis or that the null hypothesis is true, because it could be over here to the left, just a little. I just did not find enough evidence to dispute this claim. I did not get a sample in the rejection region. Let me give you a real life example. Think about it this way. What if, let me actually do another picture for it. What if this is a picture of all of the data, all of the evidence for O.J. Simpson's murder, the murder case in which O.J. Simpson was accused of murdering his ex-wife, okay? So what is the null hypothesis in a murder case? That the defendant is innocent, okay? And so if we happened to get a sample up here, okay, so if we, here is our rejection region. And so if we get a sample up here in the rejection region, we get enough evidence, then we will reject his innocence and say that he is then what? Guilty. Well, guess what happened in the O.J. Simpson case? Okay, maybe we got that. So I got that. Was that enough evidence to reject his innocence? Was that enough evidence to say he's guilty? Okay, here I was not over here, so I did not have enough evidence. So not enough evidence to say guilty. Okay, not enough evidence to say he was guilty, but listen up. Does this mean that the null hypothesis is true? It does not. Does that mean that I accept his innocence? I don't. I personally don't. They just didn't have enough evidence to reject the null. It doesn't necessarily mean that the null hypothesis is true. Okay, so that's why I don't ever say I accept the null or that the null hypothesis is true. Those are dirty words. Dirty words. I need to make a dirty word wall, and that would be one that goes up there. Okay? And dependent. You can't say things are dependent on the other. All right, let's do our picture down here. Okay, so let's draw our p-value down here. Our sample is in the rejection region. So here is our p, and the p-value is the probability of getting this sample or something more extreme if the null is true. So there's our p-value. So let's now discuss this p-value and its relationship to alpha. So this p-value, how does that size of that probability compare to the rejection probability? It's less than. Good. So our p-value is less than alpha. So since our p-value is less than alpha, that is telling me that my p-hat is located where? Is in the rejection region. Yes. Is in the rejection region. Okay? So my p hat is in the rejection region. That's what the p-value being less than alpha is telling me. So if it's in the rejection region, what will be my decision about the null hypothesis? What will I do to the null hypothesis? I will reject your claim, and I will say the alternative is correct. So I can say I have evidence of the alternative. So I reject your claim and say that it's actually something else. Okay. So now, in summary on this one, if the p-value is low, then what will we do? Okay, we'll reject HO. Yes. You know, I have not even ever come across a problem where it equals alpha because it's always a decimal in the tenths or hundredths or whatever off. I mean, I can't even imagine it coming out to be exactly. Okay, so don't worry about it equaling. But let's sing our rejection song. Okay, so we'll draw a picture of what it looks like when you are rejecting down up right here. Okay, so here we go. Very good. So there's that one. And then we're going to do our final concept of statistically significant. And so what has happened is up here, this sample, if our sample is in the rejection region, then it is considered statistically significant. Okay? And I know that the Star Spangled Banner and this song itself is a little dramatic, but it kind of, all the words in it just are so right on to what this definition is. Statistically significant. Okay, so statistically significant happens because the data you got, the sample that you got, is so far away from what was expected. So far away from expected. Okay, there's not really a way that this sample you got just happened because of chance. All of these ones in the middle, those are the ones that happened because of chance. These are the ones that happened just because of sampling variability because you got different data than me. So if my sample is in the rejection region, then the data that I got is statistically significant. Okay, so I just kind of did a short of all the words of the song. Let's see here. Where did my page go? Here we go. Let's try this. Okay, so here's our picture of our statistically significant data, and you got to be dramatic and sing the Star Spangled Banner with me. Here we go. Statistically significant happens when you're observed is so far away from expected. There's not really a way that the sample I got happened because of chance, So Statistically significant. Need some cymbal crashes on that or something, right? Okay. So you can take care of the cymbal crashes on that. Perfect. Okay. All right. So in summary, there's all our things: our p-value, our alpha, p-value's low, and statistically significant. So you understand all the basics of hypothesis testing. So let's go to the problem that we did yesterday, and I don't think we completely finished it. This is on page 21 in your packet. All right. Okay, so here is this problem where we started off. Let's recall this is about the jury, people that come in for jury duty and the proportion of them that are Hispanics. We got all the way down. Y'all help me. Did we get down to our p-value, or what did we get to? Gotcha. Okay, so we did our test statistics. So let's recall that the phantoms model, P was the parameter. We said P equals the proportion of whatever. H were your hypothesis statements that you learned how to do yesterday. A is those assumptions and conditions. Okay? N was the name. So in the phantoms model, N was the name. T is the test statistic. For us right now, that's our z-score. There are also t-scores and chi-squareds and other ones that you can get, but that's why it doesn't just say a z there. It says test statistic. So that's what we got, is that one. And then, so we got our test statistic, and we're going to obtain a p-value. And the p-value is the probability of getting this sample or something more extreme. Since we were wondering about it being too low, more extreme goes down. If we were wondering about it being too high, or wondering if we got something much higher, then my area, I would calculate the area up here. Okay? So this way, I calculated norm CDF from negative 99 to negative 1.49. I got 7.9%. So my p-value of 0.079 is greater. If it's greater than alpha, then my p-hat is not in the rejection region, so I do what? Fail to reject the null. Now, I want to write a summary of the things I want you to include in your I want to write a summary of what I want you to include in your statement. Okay, so here we go. In your conclusion, I want you to first start out with the, you're going to say since the p-value and compare it to alpha. Okay, so here's the outline of what your conclusion will contain. Since the p-value is something alpha, whatever. Then your decision. You reject or you fail to reject. Your decision about HO. But I want you to state HO in words. Okay, so let me demonstrate. So here's how the conclusion went. First started out, since the p-value is greater than 0.05, so that was our first, since the p-value is greater than 0.05, alpha, here's my decision. I failed to reject. Okay, now I recommend that you go up here to the top and regurgitate this information from what you've already written. So I failed to reject. Now I'm going to regurgitate. And we said this is from here, that the proportion of residences that are called in for jury duty that are Hispanic, so I'm regurgitating that, is 19%. So I just restated HO in words. So I failed to reject, restate that in words. Okay, and finally, I want you to give me information about if you have evidence or not of the alternative. So let's have a little small discussion about this. Okay? If I'm okay with the HO, do I have evidence of the HA? If I'm okay with HO, do I claim HA? No. So then I say I do not have evidence of HA. Okay? Okay, now watch this. Let's do another one. If I reject HO, do I have evidence of HA? Yes. If I reject, so this one, you have no evidence of HA. And if I reject the null, then I have evidence of HA. Okay, so make your last statement about if you have evidence or not of the HA. And that, you're going to just kind of have to use your common sense on that to help you through that. I don't have a song to help you remember that. Okay. Done. So now I'm just going to do problem number 1 of your homework with you. Okay? So that's on page 34. So I'm kind of this year condensing the notes, and so you have a lot of extra stuff in your packet that I'm going to get rid of for next year. So let's go over to page 34 and do the very first problem of the assignment together. I think you kind of like it whenever we do part of the actual homework together, right? That's helpful. So let's just do that. They're lengthy problems, so I have a little sympathy for you, so that's what we're going to do. Okay, so number 1. In the 1980s, it was generally believed that autism affected about 6% of the nation's children. Some people believe that the increase in the number of chemicals in the environment has led to an increase in the incidence of autism. A recent study examined 384 children and found that 46 of them showed signs of some form of autism. Is there strong evidence that the level of autism has increased? So can I say now that there is more than 6% children of the nation that have autism? So it tells me to use an alpha of 0.05, which is the default anyway. So on this next page, I've got your phantoms model. Okay, so I give you a phantoms template for everything. Okay, not all the time, but at first when we're learning. All right, so problem number 1 is about the autistic children. Okay, so I want you to right now take a moment and reread the problem. Write down your parameter, your hypothesis statements, and your assumptions. Okay, I'm going to give you a few moments to do that, and then we'll check those. So take a few moments, do the parameter, hypothesis, and assumptions now. Let's go ahead and go over what you got. See how you did. Okay, so this problem is about what parameter? What parameter are we talking about? Good. The proportion, true proportion, or the proportion of the nation's children that have autism. And we're starting off with the saying that it's the same as it was in 1980. And so what would we say for our null hypothesis? That it is at 0.06. Okay? So our null hypothesis is always our equal to. All right. But with they are wondering if it's still that way. They are thinking that it might have what? Okay, so they're going to see if it's significantly higher. So we're going to see if it is greater than. All right, so there's our parameter and hypothesis statement. So P and H. And A is the assumptions, so that's our get real. And our first one is that we have randomly selected children. So we assumed that we have randomly selected children because it didn't tell us. So we're assuming that we have randomly selected children. It's pretty much the way I want that to be said. Okay, independent. N is less than 10% of the nation's children. So 384 is less than 10% of nation's children. Nope, of all the children, because I'm sampling children. 384 are just children. Okay, now, large enough. I'm going to tell you right now that this is where I sometimes make a mistake and I put the wrong proportion. We have true P. It's a hypothesized true P, but you should use N times true P of 0.06 and N times the 1 minus P. Okay? Yes, ma'am. Because why we use P and not P hat or whatever? Okay, because you always go with what the claim is, not based on what your sample is. Because what if I'm seeing if it's completely nothing? Then I could get 0 children with autism in my sample. So I don't want to go, if I have true P, that's what the best it can be. And that's what I want to go with. Only if I don't have that do I go with the P hat sample information. Okay, so if that doesn't equal greater than or equal to 10, then I should say to myself, oh, I better sample more than 384. Maybe I need to sample 500 so that it's large enough. For example, whenever we did our M&Ms, I knew that it was 20% blue, so I knew we had to do 50 M&Ms or more, so that 50 times 0.20 was 10. So that gave me an indication of how much I knew we needed to have minimally. Okay? And so the normal model applies. All right, so that's P, H, A of the phantoms model. N is the name, and our name that of what we're doing is a 1 proportion Z test. Okay? T is the test statistic. So what is the test statistic that we get? A Z score. Very good. So we get our Z score by doing P hat minus the P over the standard deviation of P hats. Okay? So I'm going to take a moment and let you figure out those numbers. So compute your Z score now. Okay, you want to go ahead and check because you might be freaking out a little bit. I want to make sure that you got your standard deviation correct, because I'm really bad about messing that standard deviation up. Let me pull this down here. I'm really bad about putting the wrong thing in for my standard deviation. So I got my P hat from my 46 over 384. I probably should have rounded that to 0.12, but I was being all exact and everything. I have a habit of, since I just wrote down that number, sometimes I put that number in my standard deviation. So be mindful, don't do that. I've had to go back and fix my answer keys because I do that sometimes. Make sure you put true P in here for your standard deviation. Okay? So I got that 0.012. Now, if you had done 0.12 here, I was just wondering, if you did 0.12, you did P hat minus P over standard deviation, what Z score did you get? 5, like exactly? Oh, okay, yeah. See, so I got just a little less than 5, but pretty much 5. So what do you have to say about that standard deviation? That Z score? Holy cow, right? Yeah. I want to show you a picture of it. Here's what's happening. So this is where the data is located if all the samples that I would take if the samples I get center around 0.06, that's where all the samples would be located. And then here's the rejection region. Look at where I got my sample. Way out here. So norm CDF, since it's an upper bound, more extreme goes up. So my question is, how much area is up here? What's the p-value? Yeah, the p-value is pretty much 0. So the p-value is the shaded area above my sample. So it's pretty much 0%, because if you did it in your calculator, you get something like 3.9 times 10 to the negative 7th, or something really strange. So there's basically nothing above my sample. So is this considered statistically significant? Heck yeah. It's so far up there, I pretty much say what about this null hypothesis? There ain't no way that the data is centered here. I think this is so far out here, the data has surely got to be centered somewhere in this vicinity. I don't know what it is, but I don't know exactly what this is, but the data really should be in this vicinity, not down here where you claim. Okay? All right, so therefore, let's look at exactly how we write that up. So our p-value is about 0, which is less than alpha. Our p-value is low, so we reject HO. And then I say, since the p-value is less than alpha, I reject that, and I go regurgitate the null hypothesis in words. I reject, I regurgitate that, I reject that the proportion of the nation's children with autism is 6%. I reject that. And then, because I'm rejecting that, I have evidence to conclude that p is greater than 0.06. Okay, so there is the outline of how I do a conclusion. By the way, I did want to ask one thing. Can I say that the chemicals are the cause of that increase? No. All you have, quote unquote, proven is that it has increased. You don't know what has attributed to that. It could just be better identification of the symptoms. It could be the people who think it's vaccines. Okay, that's a big old debate. Okay, and I'm not saying one way or the other. Could be that. You don't know that chemicals in the environment are the reason. But anyway, okay, so what I want you to do for your assignment is this here, but I want to shorten it and have you do just 2 through 5. So you're just going to do 4 problems because they're pretty long, and we've done one together, so you don't just do those 4. And then I do have one other thing that I have to tell you about number 3. Sorry, number 3 is weird because it does not give you the population P outright. You have to think about it. So let's start number 3 together. Okay? Number 3 says this. During the 2000 season, the home team won 138 of the 240 regular season games. I don't know if this is talking about all of the MLB or just one home team or what. Is this strong evidence of a home field advantage? So let's first talk about number 3. Number 3 is saying this. P is the proportion of regular season games won by the home team. Okay, P is the proportion of regular season games won by the home team. So I have to start number 3 out for you because it's kind of strange and I don't want you to get too stumped. Okay, let me ask you this. If you do not have a home field advantage, if everything's just regular, what proportion will you win at home and what proportion will you win away? 50%. If there is no home field advantage, you win 50-50. So if the null hypothesis is that P equals 0.5. If you have a home field advantage, what are you winning at home? More than 50%. So if you have a home field advantage, P is greater than 0.5. All right. Sorry I kept you to the bell, but there you go. That's the finish of that.